Computer communications and networks, block 5, fundamentals of data communication. So in this block, we are going to discuss the 3 units, unit 15, unit 16 and unit 17. Unit 15, analog and digital transmissions, transmission impairments. Unit 16, signal encoding techniques, digital data and digital signals. Unit 17, multiplexing. So before going to start the digital transmission and analog transmission, first we are going to see what is analog signals and digital signals. An analog signal means it's a signal and a wavelength. It's a transmitted over a communication line such as the sound of voice over a telephone line. With the computers, a dial-up modem is an example of a device that takes digital data as a input and it converts into an analog signal to transmit over the phone lines, because phone lines only send the analog signals. So the next one, digital signal. A digital signal means it is a signal that represents the data as a sequence of discrete values. In this digital signal, it can take only on one value from a finite set of possible values at a given time. So this is the example of analog signal and digital signals. The first diagram, it shows the analog signal. The second diagram, it shows the digital. Okay, so the analog signal, it consists of waves. Digital signals is a discrete continuous values. It takes a one value at a time in the finite set of values. So next we are going to see analog transmission. So analog transmission means we are going to use a analog signal and transmit it over from one place to another place. To send the digital data over a analog media, it should be converted into a analog signal first. In this category, there are two cases according to data formatting. The first one is band pass, the another one is low pass. Band pass means the filters are used to filter and pass frequencies of intersect. A band pass is a band of frequencies which can pass the filters. The low pass means it is a filter that passes the low frequency signals alone. When digital data is converted into band pass analog signal means it is called as digital to analog conversion, because the digital data is converted into analog format. The second category, when low pass signal is converted into band pass means it is called as the analog to analog conversion. Next one, digital transmission. So digital transmission means is a type of signal transmission in which the signals vary discretely with the time between two values. Here we are using two values. One is known as 0. The another one is representing as 1. Here one representing the binary number 0. The another one representing the 1. The variable quantity in copper cabling is generally the voltage or electrical potential. In this case, variation in the intensity or any other physical quantity, it is utilized in fiber optic cabling, otherwise or wireless communications. For transferring a binary information through any particular communication channel, such as a network cable or telecommunication link, digital signals employ a discrete values. A digital signal is transferred one bit at a time on a serial transmission line. Next one, transmission impairments. So what is meant by transmission impairments means in a communication system, analog signals will travel through the separate transmission medias, which tends to deteriorate the quality of the signals. So which means the signal at the beginning of the medium is not same as to the signal at the end of the medium. That means when information is transmitted from the source side, during that time the signal value may not be the same at the receiver side. So maybe the imperfection causes during the signal impairment. So some of the causes are there in the impairment. So what are the causes are there means three types of causes are there. The first one attenuation, second one distortion, third one is noise. So the first one attenuation, that means loss of energy. The strength of signal decreases with the increasing distance, which causes the loss of energy in overcoming resistance of medium. So this is known as the attenuated signal. So during this problem, we are going to use the amplifiers. The amplifiers are used to amplify the attenuated signals, which gives the original signal back and compensate for this loss. So this is the example of the attenuation. So the first one is for original signals, that is for analog waves. That particular original signal can be attenuated, that should be represented the second diagram. Using here amplifier, that should be converted into the attenuated signals into normal signals, that is for amplified output. So this is the logic gate 0.1 to 0.2. We are going to use transmission medium. So maybe in between of 0.1, 0.2 and 0.3, any one of the places the signal can be attenuated. So to overcome the issue, we are going to use the amplifier that can be overcome the issue. So at the reaching of destination 0.3, the original signal can be retained. Attenuation is measured in the decibels, that may be represented as dB. It measures the relative strengths of two signals or one signal at a two different points. So attenuation of dB equal to 10 log 10 of P2 divided by P1. P1 means it is the power at the sending end. P2 means it is the power at the receiving end. Somewhere the decibel also defined in terms of voltage instead of the power. In case the power is proportional to the square of voltage, the formula is used as attenuation of dB equal to 20 log 10 of V2 divided by V1. Here V2 means voltage at the receiving end, V1 means voltage at the sending end. P means it represents the power, V means voltage. So the second one, distortion. Distortion means changes in the form or shape of the signal. So this is generally happen in the composite signals. It made up of with different frequencies. Each frequency component has its own propagation speed traveling through a medium. So based upon medium, it may be different propagation speed. And that's why it is delay in the arriving at the final destination. Every component arrive at different time, which leads to the distortion. So therefore, they have different phases at the receiver end from what they had at the sender's end. So this is the example of sender end and receiver end. So the first one, the composite signals is sent by the sender, that can be converted into different frequencies at the different phases. Here I am going to use three components in the phases. Based on frequency level, it converted into different waves. It can be transformed to the receiver end. Separate signals are converted into again single composite signal. So what the signal sent by the sender, the same should be received by the receiver. So third impairment is noise. So the noise means the random or unwanted signal that mixes up with the original signals is called as the noise. So therefore, several types of noise such as induced noises, thermal noises, and impulse noises. These noises are corrupt our original signal values. So now I am discuss what are the different types of noises are there. The first one is induced noise. Induced noises are come from the sources such as motors and appliances. So these devices act as a sending antenna and a transmission medium act as a receiving antenna. The second category is not thermal noise. Thermal noise means it's a movement of electrons in wire which creates an extra signals. The third one is crosstalk noise. Here when one wire affects the other wire means the crosstalk noise will happen. The fourth one, impulse noise. Impulse noise is is a signal with high energy that comes from lightning or power lines. So that when the during the rainy time lightning, that moment impulse noises are created in our signals. So this is the example of noise. First one, during the information or transmitted between point 1 to point 2, the first original signal is transmitted. Next one, in the original signal, some of the any one of the type of noise is added. So our original signal is converted into noise voice, noise signal that should be transmitted to the point 2, that is for destination side. So to find the theoretical bit rate limit, we need to know the ration. The ration it is used to find out the signal to noise ratio. That should be defined as SNR. That means signal to noise ratio equal to average signal power divided by average noise power. So here calculated as what is the original in signal transmitted and what is the signal can be received. So according to that, based on signal to noise ratio, it is easily identified by how much amount of signals are affected by noise. So next topic, next unit, signal encoding techniques. So before going to start signal encoding techniques, first I am going to tell about what is meant by encoding. So encoding and decoding. So encoding means it is the process of converting the original data or a given sequence of characters, symbols, alphabets, etc. into a specified format. For what purpose it is converted means for the secured transmission of information from one place to another place. So our original data is converted into some other format, either it may be a character, symbols, alphabets, or whatever may be. So this is called as the encoding. So next one, decoding. So what is the mean by decoding means it is the reverse process of encoding. What is done at the encoding side, that should be reversed. So which is to extract the information from the converted part. So in sender side, what are the original information is converted into some other format, other converted format, that is to be transmitted to the destination. In destination side, we are going to do the decoding. Here the converted extracted informations are converted into the original format. So next I am going to tell about what are the signal encoding techniques are available. So we are going to use 4 different types of encoding techniques are available. The first one, digital to digital. Second one, digital data to analog signal. Third one, analog to digital. Fourth one, analog to analog. So the first one I am going to tell, digital to digital conversion. The representation of digital information by a digital signal is known as the digital to digital. That means source also digital, the receiving end also digital. The process of converting binary ones and zeros created by a computer into a series of voltage pulses. Okay, then it can be transmitted across a wire. This is known as the digital to digital encoding. First, our binary bit pattern, that means zeros and ones created by the computer, everything should be converted into the voltage levels. Okay, so the voltage levels only transmitted across a wire. So this process is called as the digital encoding. This process also known as line encoding. So this is the different categories of digital to digital encoding. First one, unipolar. The voltage pulses are sent via a connection such as wire or cable or any one of the digital transmission system. In most of the encoding schemes, one voltage level represents 0, the another voltage level represents as 1. Each pulse polarity decide whether it is a positive or negative value. Because it only employs only one polarity, this form of encoding is known as a unipolar encoding. The polarity is allocated to the one binary state is in unipolar encoding. Ones are represented as positive values, zeros are represented as a 0 values. In unipolar encoding, 1 represents the high voltage and 0 represents the 0 value. That means nothing in the digital encoding. Unipolar encoding is less complicated and less expensive to
implement. So this is the example of digital unipolar encoding. Here one represents the positive value, zero represents the zero value. That means wherever one is there, based on the amplitude, here only the digital signals are generated. So wherever zero is represented, here that represents the zero value. That means no digital signals are generated. The second category is polar. To encode a binary values, the polar encoding techniques utilize several voltage levels. There are three different types of polar encoding schemes are used. The first one is for N or Z. The second one is for R Z. Third one is for bypass. N or Z means non-return to zero. R Z means return to zero. Bypass. These three are the polar encoding techniques. N or Z means non-return to zero. So non-return to zero, it represents the binary values using two different distinct voltage levels. In general, positive voltage equals to 1 and negative voltage equal to 0. It is also called as N or Z due to the lack of rest conditions. In the N or Z scheme, it has two types. One is called as N or ZL. The another one is called as N or ZI. N or ZL means it adjusts the voltage levels when a different bit is deducted. N or ZI, it switches voltage when one is deducted. Next, second category, R Z. R Z means return to zero. It is used to establish synchronization. Each bit must undergo a signal change. In order to have a change in with every bit, we must have three values that is represented as positive, negative, and zero. So these are the three values are used in return to zero. RZ is a three value encoding method in which positive voltage represents 1, negative voltage represents as 0, a zero voltage indicates none. So three values are used here. One is positive, another one is negative, the third one is 0. In RZ is a three value encoding method. 1 means it is a positive value, 0 means negative value, 0 voltage indicates the none. In the RZ system, the signal returns to 0 halfway through each period. In RZ scheme, 1 bit is represented by a positive to 0 and 0 bit is represented by a negative to 0. So the third category is biphase. So biphase encoding is a type of encoding in which the signal changes in the middle of the bit interval but does not return to the zero. This is called as the biphase. In this biphase, two different types of biphase encoding schemes are used. One is called as Manchester encoding. Another one is called as a differential Manchester encoding. So the third category is called as bipolar. Already we discussed unipolar, bipolar. Third category is bipolar. A positive, negative, and zero voltage levels are represented using the bipolar encoding methods. The zero voltage level represents the binary value of 0, while the binary 1 is represented by alternating positive values and negative values in bipolar encoding method. If the first 1 bit represents positive amplitude, the second 1 bit represents the negative amplitude. The third one represents the positive amplitude, so on. Even if the 1 bit are not consecutive, this alternation can occur. Okay, all of you clear? In this category, 0 voltage, it represents the binary value of 0. 1 is represent the alternative positive and negative values. This is called as the bipolar encoding method. First bit represents the positive amplitude. Alternatively, the second bit represents the negative value. Third one, again 1 means it represents the positive amplitude. Next one is for negative voltage. And the same process it goes on. Even if the 1 are not consecutive, this all okay, not 1 or consecutive, not 0 is consecutive. It does not, this alteration can occur. Okay, so the second category is up to this.
Digital to digital conversion is over. The next one is for digital to analog conversion. So the input is in a digital format, the receiving end is a analog conversion. When data from one computer is sent to another, some analog carrier, if the first converted into analog signals are modified to reflect digital data. Analog signal means is a characterized by its amplitude, frequency and phase. Three category. There are three kinds of digital to analog conversions are there. The first one is called as amplitude shift keying. Second one is for frequency shift keying. Third one is called as phase shift keying. These three techniques are used for digital to analog conversion. So in this first one, amplitude shift keying. In this conversion technique, the amplitude of analog carrier signal is modified to reflect the binary data. This is the example of amplitude shift keying method. So based on time and amplitude, the graph will be generated. When binary data represents digit 1 means the amplitude is held, otherwise it's set to 0. If amplitude is not set means it is represented as 0. Wherever 1 is presented in the graph, here the amplitudes are set. So both the frequency and the phase remain same as in the original carrier signal. So this is known as the amplitude shift keying. In the diagram, first value 1, next 0, 1, 0, 1. So 1 means the signal, amplitude signals are generated. 0 means there is no signal. Next one, frequency shift keying. In this conversion technique, the frequency of the analog carrier signal is modified to reflect the binary data. This technique uses two different frequencies. One is called as F1, the another one is called as F2. One of them, for example, F1 is chosen to represent binary digit 1 and other one is used to represent the binary 0. So the both amplitude and phase of the carrier wave are kept intact. So this is the diagram example of frequency shift keying. Here we are going to use two different frequencies. One is known as F1, the another one is represented as the F2. The single small amplitudes are represented as F1. The biggest amplitudes are represented as the F2. The third category, phase shift keying. So in this conversion scheme, the phase of the original carrier signal is altered to reflect the binary data. When a new binary symbol is encountered, the phase of the signal is altered. Amplitude and frequency of the original carrier signals also kept intact. Here, this is the example of phase shift keying. So based on time and amplitude, according to the signal value, it can be generated. The values of the phase shift keying value is 1, 0, 1, 1, 0. So according to value 1, 0, 1, 1, 0, the signals are generated. So the third conversion is analog data to digital conversion. So analog to digital conversion occurs when analog original signals are converted into digital form. That means input signals or analog signals, the output is a digital format. Assume a human delivers a speech in the form of analog signal. It is a voice. It must be digitized the analog signals to make it less susceptible to noise. It is necessary to reduce the amount of values in an analog message in order for them to be represented in the digital form. So the information contained in the continuous waveforms first is transmitted into a digital pulses during the analog to digital conversion. So what are the different categories are used for analog to digital conversions means two different categories are used. One is known as PAM, PAM, the another one is called as PCM. So the first one, PAM, means pulse amplitude modulation. The another one is for PCM, means pulse code modulation. Pulse amplitude modulation is a analog to digital conversion method. In this method takes an analog signal for first
takes an analog signal. Next, it is samples it and then creates a sequence of digital pulses based on the sampling results. After that, the sampling involves only for measuring the amplitude of the signals at the particular intervals, equal intervals. The PAM method is ineffective in data transfer because it converts the original waveforms into pulses that are not the digital signals. PAM techniques is changed to PCM technique, then only it is possible to make them into a digital signals. So the second category is for PCM, pulse code modulation. So the pulse code modulation method is converts the PAM pulses. PAM means pulse amplitude modulation pulses into a digital signal. After that, in the PCM quantizes first PAM pulses, then the technique of assigning integral values in a particular range for the purpose of sampled instances. So this process is known as a quantization. So PAM quantization, binary encoding and digital to digital encoding, these are the 4 different operations or makeup in the pulse code modulation. So what are the 4 methods are used here means PAM quantization, binary encoding and digital to digital encoding. These are the 4 operations to performed in the PCM, pulse code modulation. So the fourth category, analog data to analog signal conversion. So analog to analog conversion or modulation means it is representation of analog information by an analog signal. It is the process of which characteristics of carrier wave is varied according to the instantaneous amplitude of the modulating signals. The modulation is generally needed by the band pass signals. Band pass is a range of frequencies. It is used to transmitted through a band pass filters, which is the filter. It allows the only specific frequencies to pass, preventing signals at unwanted frequencies. So what are the methods are used for conversion of analog to analog means here we are going to use 3 different techniques. One is called as amplitude modulation, that is AM. The second one is frequency modulation, FM. The third one is phase modulation, PM. So the first one, amplitude modulation. So the modulation in which amplitude of the carrier wave is varied according to the instantaneous amplitude of the modulating signals, keeping phase and frequency as a constant value. This amplitude modulation is usually implemented by using a symbol modifier because the amplitude of the carrier signals, it should be needed to change according to the amplitude of the modulating signal. So this diagram, it shows the example of amplitude modulation. So the first one, modulating signal I specified. Second one is for carrier signal, our original signal. So this is the output of amplitude modulation. Here our carrier signals are converted into modulating signals, combined. Both the modulating and carrier signals are combined. It produces the amplitude modulation. So amplitude bandwidth, it is used to it is used for identifying the bandwidth ratio. The modulation creates a bandwidth that is twice the bandwidth of the modulating signal and also covers a range of centered on the carrier frequencies. What is the formula for amplitude modulation bandwidth is bandwidth equal to 2FM. FM means frequency modulation. Is the double the value of compared to the bandwidth. The second one is for frequency modulation, FM. The modulation in which the frequency of a carrier wave is varied according to the instantaneous amplitude of the modulating signal, keeping phase and amplitude as a constant value. FM is normally implemented by using a voltage controlled oscillator as with FSK, frequency shift keying. The frequency of the oscillator changes according to the input voltage, which is the amplitude of the output or modulating signal. So this is the example of frequency modulation diagram modulation. So the first one, modulating signal, is specified. The second one is for carrier signal. Third one is for frequency modulated signal. So FM bandwidth, the bandwidth of a frequency modulated signal is varies with the both deviation and modulating frequency. Here we are going to use the modulating frequency MFS 0.5. Wide band of FM signal. For a narrow band frequency modulation signal, bandwidth is required is twice the maximum frequency of the modulation. However, for a wide band, this is for narrow band. Suppose it may be a wide band frequency modulation signal, means it required a bandwidth can be very much larger, which deductible sideband spreading out over the large amount of frequency spectrum. So the third category is phase modulation. Phase modulation means it is the carrier wave is varied according to a instantaneous amplitude of the modulating signals, it keeping the amplitude modulation as well as the frequency as a constant value. So which modulation we are going to calculate, that one is identified as the constant. Remaining values, remaining two things is considered as a constant value. Here phase modulation is we are going to calculate. So based on the amplitude of the modulating signal, here amplitude and frequency constant values are considered as a constant one. So the phase modulation is practically similar to frequency modulation, but in the phase modulation, frequency of a carrier signal is not increased. It is normally implemented by using a voltage controlled oscillator along with a derivative. So the frequency of the, what is the frequency available in the oscillator changes according to the derivative of the input voltage, which is amplitude of the modulating signal. So phase modulation bandwidth can be calculated. It means it is similar to the amplitude modulation AM and exhibits its unfortunate doubling of baseband bandwidth and poor efficiency. That signal is represented, the diagram is represented as phase modulation. So the first one is for modulating signal, the second one is for carrier signal. So the third one is for phase modulation. For a signal, a large sinusoidal signal, PM is similar to FM, frequency modulation, and its bandwidth is approximately 2 into H plus 1 FM, where H is identified as a modulation index. So up to this, signal encoding techniques are over. Next topic, multiplexing. So this is very important thing in communication network. So what is meant by multiplexing? Means it is the sharing of medium or bandwidth. So what is the mean by multiplexing? Means we are going to combine multiple inputs and it generates the single output. It is the process in which multiple signals are coming from multiple sources. All the multiple sources are combined into a single source. After that, it should be transmitted over a single communication link. Otherwise, it is called as a physical line. So simultaneous transmission of multiple signals across a single link is called as a multiplexing. It can utilize higher capacity links without adding additional lines for each device for the purpose of better utilization of bandwidth. So next one, I am going to tell about what is meant by many to one and one to many. In a multiplexing system, we are going to use n number of devices. The n number of devices share the capacity of only one link. For example, I am going to consider 4 devices on the left that left direct the transmission streams to a multiplexer which combines them into a single stream. So see the diagram. Here First case is called as multiplexing versus no multiplexing. Here 4 devices are there. 4 computer devices are connected to the another 4 computers. Here it is called as no multiplexing because device 1 is directly connected to device 1, sender receiver like that. In the B1 it is known as the multiplexing because all 4 input lines are combined into a one device that is called as MUX multiplexer. So here all 4 inputs are combined and generated into a single line, that means called as only one path we are going to use. It is called as one path 4 channels. Suppose I am going to use five devices during transmitted in the multiplexer, means it is represented as one path 5 channels. After that it can be transmitted to the demultiplexer side. It is the reverse process of multiplexer. So the single path inputs are again separated and transmitted to the corresponding destination. So one is converted into 4. So this is the diagram example of multiplexer. Here I am going to use n number of inputs is combined by a multiplexer. So everything should be transmitted into a only one link. Using the one link, we are going to use transmit any number of channels input. After that, in the destination side, we are using demultiplexer that is converted into the separate outputs that is called as n outputs. That thing only specified in this slide. The 4 devices on the left direct the transmission streams to a multiplexer which combines them into a single stream that is called as the many to one. 4 devices are combined. So next one, the multiplexer MUX on sender side. Demultiplexer is shortly represented as DEMUX. It separates this transmission stream and direct signals to a intended corresponding receiving devices. So here path means it is identified as the physical link. Channel means portion of path that carries a transmission between a given pair of devices. Here one path can have n channels. Next one, what are the different types of multiplexing are available? The first one is called as frequency division multiplexing, FDM. The second one is wave division multiplexing, WDM, wavelength division multiplexing. Third one is time division multiplexing, TDM. So the same thing is represented in the diagram. Again, time division multiplexing is divided into 2 categories, synchronous TDM, another one is asynchronous TDM. So the first one, frequency division multiplexing. So the frequency division multiplexing is an analog technique. It can be applied when bandwidth of link is greater than the combined bandwidth of the signal is transmitted. Suppose a signal from each sending device modulate different frequencies. After that, the modulated signals are combined. It is converted into a single composite signal. So the bandwidth ranges or channels through which the signals can travel. Channels must be separated by strips of unused bandwidth that is called as the guard bands. So the guard bands is used for prevent the signals from overlapping. So the overlapping, to avoid the overlapping process, we are going to use the guard bands. So this is the FDM process. So analog to analog signal. So the 3 devices are connected. So the 3 channels are combined by the multiplexer, channel 1, channel 2 and channel 3. Every channel's output can be transmitted to the demultiplexer. Again, it can be converted, decoded into the destination side. The transmission path is divided into 3 parts, each representing a channel to carry only one transmission. So what is the FDM process here? Means it is the analog process. Here telephones are used as the both sides as input as well as output devices. Here each telephone, it generates a particular signals of same frequency range. Inside the multiplexer, here these three similar signals are modulated into a different carrier frequencies. The different carrier frequencies namely represented as F1, F2 and F3. So the resulting modulated signal again are combined into a single composite signal that is sent over to a medial link that have a enough bandwidth to accommodate that particular single composite signal. In the destination side, we are going to use a demultiplexer that uses a series of filters that decomposes the signals. So this is the example of frequency division. This is for sender side. So I am going to use three telephone lines. Each one generates the different frequency range that is represented as F1, F2, F3. After that, the three different frequencies are combined into a single combo. So I am going to combine. So that's why plus symbol is used here. So all three different frequencies, that means F1, F2 and F3 both are combined. It produces a single composite signal is a output. It will enter into the demultiplexer. That means single composite signal is entered. Here we are going to use the filters. That filters is converted the single composite signal into separated signal. So based on the frequency range, after that the same thing will be transmitted to the corresponding telephone lines. So what is generated by the sender side, according to the same signals are transmitted to the receiver side. So both time multiplexing used the time divisions. So this diagram shows the FDM and FDM multiplexing and demultiplexing process in the single diagram. Next one, what is the analog hierarchy used in the phone network? Means different hierarchy levels are used. The first one is called as generally group, next is super group, master group and jumbo group. For a group means we are minimum it required 12 voice channels. Each channel have a capacity of 4 kilohertz. So at last the output of FDM process it is called as a single group. In a single group it consists of 12 voice channels, each have 48 kilohertz frequency. After that 5 groups are combined and produce a output. It is called as a super group. The super group is called considered for 240 kilohertz and 60 voice channel. Here 10 super groups are combined and produce a one master group. One master group means it consists of 600 voice channels. The capacity is for 2.52 megahertz. After that 6 master groups are combined and produce a single jumbo group. The jumbo group consists of 3600 voice channels and 16.984 megahertz. So these are the analog hierarchy of a telephone network. So next, what are the applications of FDM? Means amplitude modulation and FM frequency modulation radio also example applications of frequency division. After that DV broadcasting and first generation cell phones also based on the frequency division multiplexing. So up to this frequency division multiplexing over, the next topic is WDM, wavelength division multiplexing. So this is used in the fiber optic cables. So what purpose it is used in fiber optics? Means to increase the capacity of the single fibers. It is a analog multiplexing technique. Okay, next optical signals from it received from the different sources, and all the different sources optical signals are combined to form a wider band of light with the help of the multiplexers. After that, use light signals transmitted through the fiber optic channels. Here, a very narrow bands of light are combined from several sources to make a wider band of light. Here, a prism is used. What purpose the prism is used? Means to bend the light beams based on the angle of incidence and frequency value. In the receiver side, they are going to use the demultiplexer for the purpose of separate the channel signals. So what is mean by receivers demultiplexer separate signals? Means at the receiving end, the demultiplexer separates the signal to transmit them from this sender side to the respective destinations. So this is the example of WDM process. The different signals are received from the different sources
So all three things are combined in here we are going to use prism. It combined and transmitted to the destination side. So what are the WDM applications are? It is used in SONET network, that is multiple optical fiber lines or multiplexed and demultiplexed. Next one DWDM. DWDM means dense WDM. It allows multiplexing of large number of channels by spacing channels closer to one another to achieve greater efficiency. So the third technique is time division multiplexing, TDM. What is the process? What is mean by TDM? Means process of combining digital signals from several sources whereby each connection occupies a portion of time in a particular link. Here all the signals operate with the same frequency, that means same bandwidth at different times. Here a link is sectioned by time rather than the frequency. Here full and full based on the time. So this is the example of time division multiplexing. Here I am going to use 4 devices destination source. Another 4 devices is considered as a destination. The data is flow from left to right. That means source to receiver side. So again I am going to use in the sender side's multiplexer. So the all 4 inputs are combined. The inputs are represented as 1, 2, 3 and 4. So based on time interval, it can be transmitted to the receiver side. So here TDM can be implemented into the 2 ways. One is called as synchronous TDM. The another one is called as asynchronous TDM. So synchronous TDM means the multiplexer allocates exactly same time slot to each device at all time, whether or not a device has anything to transmit or not. Suppose if any devices or nothing to transmit means it also allocate a one time slot. This is called as synchronous TDM. So this is the example of synchronous TDM. Here I am going to use 5 different devices. That means 5 inputs. It is represented in the different colors for identification. The device 1 is blue color, another one is red color, yellow color, green and black. So all 5 inputs are combined to generate a single time division multiplexer. That is number of input is 5. Number of slots in each frame is called as 5 because each time slot have a different frames because it received from 5 different devices. Suppose I am going to use 4 number of inputs means here number of inputs is 4, number of slots in each frame is 4. So based upon your input devices, number of input is differ as well as number of frame also differ. Okay, so first one here I am going to use 5 inputs. So number of input is 5, number of slots in each frame is 5. So the frame 1 it consists of again the same order, blue, red, yellow, green and black. The same order is followed by the n number of frames. So the next one, what is meant by time slots and frames? So data flow of each connection is divided into separate units. Link is used for combines of 1 unit of each connection to make a frame. Here I am going to use n number of input connections. So it generates the n time slots. Data rate of link must be n times the declaration of a time slot to guarantee flow of data. Time slots are grouped into frames. One complete cycle of time slots, each slot decided to one device. This is the example of time division multiplexing. So I am going to use 3 different devices. A1, A2 and A3. Next B1 is not there, B2, B3. Next one is for C1, C3. Data are taken from each line every t seconds. I am going to use here 3 t seconds. So the first frame here how many devices I am going to use means 3 different devices. So each frame consists, each slot consists of 3 frames. So first one A1, A2, A3. So listen, A1 it taken based on the t seconds, both 3 devices A, B, C, that is the order. In the frame 1 3 slots are there. First one is A1 is available, next A2 is not available, so it is treated as a empty. After that C1 is available, so the first frame is over. So the next frame again it starts from A device, the input is A2, another one is B2 available, C is not available, it is treated as empty. So the frame 2 is over. Next, third frame, again it starts from the first input A3, B3 is available, C3 also available. Here, each frame has a 3 time slots. Each time slot duration is treated as a T second. Suppose if time slot is present means it is added into the slots. Suppose if frames are not available means it is added in the empty slots. Next one, interleaving. So what is meant by interleaving means a process of taking a specific amount of data from each devices in a regular order is known as a interleaving. May be done by bit, byte or any other data units. So here I am using a synchronization concept. The previous example is followed here. 3T time intervals A1, A2, A3, B1 is not there, B2, B3, C1, C3. So during the synchronization, first frames are generated. First A1, A2 is not there, C1. In frame 2, A2, B2 is available, C2 is not there. In frame 3, A3, B3 and C3 are available. This is for synchronization. It is transmitted to the receiver end. Here is desynchronized. It is converted into the same order. A1, A2 is not there, C1. The next one is for A2, B2, C2 is not there. Next frame 3 is for A3, B3 and C3. So this is the another example of time division multiplexing. So first I am going to consider here 4 different outputs A, B, C, G. In A, it consists of 6 A's available. In B, 3 B's, C, 4 C's, D, 5 D's are available. So I am going to use the multiplexer. It is generated into the different time slots. In each frame consists of number of slots is 4. First, I am going to choose starts from first device A. So A, B, C, D, the first frame is over. The next it starts from second time slots A, B, C, D. The second from also over. On next step it starts from third T, that is for A, B, C, D. That also third from also over. In fourth frame it starts from A. 4A is available, B is not available. So A present, B is absent, C available and D available. So fourth frame is over. Next in the fifth frame, A is available, B not available, C not available, D alone available. So and A and D is present in the time frame. After that, in the last frame, the only A alone available, remaining B, C, D is not available. It is treated as empty. So this is for multiplexing side. In the demultiplexer means it is the reverse process. Here, what is the last input output A, AD, the same order can be transmitted to the receiver. Here it is demultiplexed. It is transmitted to the receiving end A, B, C, D. So first frame over, next another A, B, C, D, next A, B, C, D. Next fourth frame A available, B is not available, C, D. In fifth frame A and D fixed. Now last frame A. So it is similar to what is after completion of demultiplexer process. The same is followed by a sender side. In sender 5 during 6 time slots, 6 A's are transmitted. Here 6 A's are received. So the same thing, 3 B's are transmitted in the sender side. The 3 B's also received in the receiver side. Next 4 C's are transmitted, 4 C are received. Here 5 C's are received, transmitted. The same 5 C's are received. So after that, I am going to tell about framing bits in a synchronizing. So framing bits means it is used to improve timing inconsistencies that may be introduced in the TDM process. Here only usually 1 or 2 synchronization bits are added to the beginning and end of the each frame that allows the demultiplexer to synchronize with the incoming stream, so it can separate time slots accurately. Alternate zeros and ones are used. So this is the synchronization patterns. That means alternate zeros and ones framing bits. For example, frame 1, A1, 0, C1, the extra bit is for synchronization bit is 1. So the next frame 2, 0, frame 3 is 1. That is for alternating zeros and ones are used. That is not, it is used for improving the inconsistencies. So based upon these bit patterns, we are going to identify the synchronized patterns. Here I am going to six slots are used from the right to left. 1 0 1 0 1 0. So the all 6 bit patterns are combined. Finally, I got 0 1 0 1 0 1 is treated as a synchronization bit patterns. Next one, bit padding. Bit padding is used when different speeds of devices are not integer multiples of each other. That is, a device A may be 5.5 times as fast as the device B. Multiplexer adds extra bits to a device source stream to force the speed relationship between devices into integer multiples of each other. Each extra bits are discarded at the destination side, that is for demultiplexer side. So up to this synchronization TDM is over. Next one is for asynchronous TDM. It is also called as the another name statistical TDM. It is used for designed mainly avoid the waste. Here we have n number of input lines. The frame contains no more than m slots, which m is less than n. Compare with the synchronous TDM. Here number of input, according to number of inputs, number of slots are used. But in the asynchronous TDM, now n input lines, it should be lesser than the m value. In asynchronous TDM supports same number of input lines as synchronous TDM with a lower capacity link. Here I am going, this is the example of asynchronous TDM. Here I am used 5 different systems. After that, the same process is followed, multiplexing. So here number of inputs is 5. Here number of slots in each frame is 3. I specified 3. So frame 1 only 3 frame, frame 2 is 3 frame, etc. up to frame n also 3 frames. For example, I am going to use 5 devices A, B, C, D. Here A present, B is not there, C and E. In the previous example, I specified in each frame consists of 3 slots. Okay, so I am specified here A1, and next one is for C, the corresponding device number is 3, E5. So A1, C3, E5. So the first frame is over. The second frame again A1, C3, E5. Third frame again A1, C3, E5. Fourth frame again A1, C3, E5. Okay, up to this over. Next, last fifth frame, this is for only 2 A's is available. In the synchronous TDM, the frames are not available, means the spaces are allocated, but here there is no space. Continuously, we are going to represent the asynchronous TDM slots. Here 2 A's are available. So I am specified A1, A1, again one slot also empty. In the destination side, this is the another example. Here A, C, D, E is available. In each time slot also, I am going to consider only 3 frames. So A1, C3, D4. That's it. Only 3 frames. After that, E will be represented in the next slot. So E5, again A1, C3. So second frame is over. So the next one is for D4, E5, A1. So the same order will be followed. So the next example, all 5s are present. So the same thing should be, because all 5 lines are sending the data, but previously I specified number of input is 5, but number of slots in each frame is 3. So A1, B2, C3 is fixed. Next frame, D4, E5, A1, the same order will be followed. So thank you. Up to this, we are going to discuss about various synchronization techniques, transmission, digital transmission, analog transmission, and encoding techniques, multiplexing also. Thank you.